When we do hypothesis testing, we are beginning with some kind of situation that we want to test. And so, for example, if we started off with a null hypothesis that says that the population mean is equal to 0, that means we're envisioning some scenario where the distribution of the population parameter is centered on 0 and then has this range of values that stretch out to the left and to the right. And under the critical value method, so the critical value method of hypothesis testing, before we even calculate the value of the test statistic, we decide where our cutoff points are. So let me explain what I mean by that. So what we would say is, okay, in order for us to establish that this is not true, it's not enough to have something that is different from 0. It has to be very, very unlikely given that the true mean is 0. So under the critical value, so we would have this, this left critical value and this right critical value such that let's say we wanted to be 95% confident that we are making the correct decision with regard to this null hypothesis. So that would mean that we want to choose left and right critical values such that 95% of the probability is in here. So that means 95% of the time, if the null hypothesis is true, that is, if the population mean is actually 0, 95% of the time we would observe a value somewhere in here, which means that we would have 2.5% of the time we would observe something out here, and 2.5% of the time we would observe a value out here. So under the critical value method, we're coming up with a left critical value and a right critical value such that, so the probability that the test statistic, so let's just call it X bar. So we're taking a sample mean here. So the probability that the sample mean falls between the left critical value and the right critical value is equal to 95%. Okay, so the probability that that sample mean is going to be in, between these two values is 95%, which means that the probability of it being outside, so the probability of that sample mean being less than, let's just keep it at less than, the probability of it being less than the left critical value or greater than the right critical value is only 5%. Okay? So by, under the critical value method, so we're able to say, okay, well, if our test statistic is greater than the right critical value or less than the left critical value, if the null is true, that would only happen 5% of the time. Now, we can't say that it would only happen 0% of the time just because of the way sampling works, and sometimes you get a weird sample, but we are saying that only 5% of the time would we observe a value outside of here. Okay, so that's the critical value method. But what if let's say we had a value let's say we observed a test statistic that was, let's say here, okay? So that would enable us to reject the null, right? Because there's only a 5% chance that if the null was true, we would have gotten this extreme of a value, right? But compare that to if we had observed a value, let's say out here, okay? So in both cases, we would reject, but if we had observed this value out here, then it would be a stronger case for rejection, right? So, the probability of being beyond here is only 5, but we would want to say, okay, well, what's the probability of it being out here versus out here? And so this is the added information that you can get from the p-value method. And so the p-value method actually tells you not just the probability of getting something beyond, the probability not just of getting something beyond the critical value, but the probability of actually observing a value this extreme, okay? So this enables us to say, okay, well, this would be a p of, this would be a p-value. The probability of observing something out here would have been, only 0.05. This would have been, say this one. The p-value for this one, there's a smaller probability, so that we might be able to say, well, that was only 0.04. But if we were way out here, we might observe the probability corresponding to that particular value is only 0.002. So you can see how having a p-value, having an actual probability, gives you a greater basis for which to make an inference about the null, to draw a conclusion about the null hypothesis. So we would reject in all of these cases, but this gives us stronger evidence for rejection. So how do we go about finding a p-value then? Okay, so just to review some of the basics here. So let's say that we calculated our test statistic. Okay, so in all of the tests that we do, there's some way of calculating the test statistic. And let's say we calculated it and it was 2.8. Okay, so in order for us to do anything with this 2.8, we need to know what's the probability of observing this extreme of value if the null hypothesis is true. And this probability is actually the p-value. So you can see that if this is low, then that is a lot of evidence that the null is to be rejected, that we can reject the null, that the null is false, null false. Okay, so that would mean, okay, we got an extremely low probability, let's say 0.0002, then we can say the probability of observing a value this extreme, if the null is true, is only this. Therefore, that's sufficient evidence to conclude that the null hypothesis is false. Okay, so this is what this is what the p-value gives us. And so how do we calculate it? The key with this is that we need to adapt it according to our hypotheses. So I'm going to go through 3 different cases to show you how exactly we calculate a p-value, assuming that we have, in all of the cases I'm going to show you, okay, so we calculated a test statistic of 2.8. What is the p-value? And the p-value is going to depend on what your null and alternative hypotheses are. Okay, so let's look at 3 different cases. So in case 1, we are hypothesizing that the mean is equal to 0 under the null, and our alternative is that it's not equal to 0. Okay, so then our distribution under the null hypothesis would look like this, where it's centered on 0, and we are interested in Okay. So we're interested in two different possibilities here, right? Because not equal could mean two different things. It could be that the mean is less than, or it could be that it's greater than 0. So under this two-tailed test, we're interested in how much area there is out here and here, where this is the probability of observing that statistic, which in our case was 2.8. Okay, so that would mean this is, was it 2.8? Yeah, 2.8. So that would mean we have 2.8 out here and 2.8, and we would have negative 2.8. So notice that we calculated a test statistic that was positive, but we are interested in the probability of a value that extreme. That is, so it can be 2.8 out here or 2.8 out here if we're only interested in the not equal alternative. Okay, so we need to have the total area here and the total area here, and we need to add those up. Okay, so this is the same, we can use the same Excel function that we used to calculate the normal probabilities before, because we are assuming a normal distribution under the null hypothesis, so we can use this function. So we use norm dist, okay, and we're using the minus statistic. Okay, that's easier because remember that this is going to give us the cumulative all the way up to whatever this value is. So this will just give us here, okay? And then this is going to be the mean and the standard deviation, and we put in true for continuous, and then we multiply by 2. Okay, so the reason we're using the -1 is it's just easier to calculate from negative infinity up to here rather than doing negative infinity up to here and then doing 1 minus that. So just doing the negative value works because it's a symmetrical distribution. Okay, so let's figure out what's the p-value then of 2.8 for a two-tailed test. So I'll just go ahead directly to Excel and do this. Okay, so it's going to be norm dist. Okay, so the x value is negative 2.8, mean 0, standard deviation of 1, and true. Okay, so this is 0.0025. So what this is telling me is that the probability of having a value in here is 0.0025. Okay, so that's how much area is here. So the probability of observing a value out here is 0.0025. But because we are interested in an extreme value in either direction, we have to add this over here. And because this is going to be exactly the same size as this, we can just multiply this by 2. And that's what I'm doing here. Okay, so 0.005. Okay. Okay, so that the p-value there is 0.005. And if we were to establish, so let's say we wanted 95% confidence, giving us 0.05 alpha. Okay, and so the question is, well, okay, so is p less than our alpha? And we see that it is. Okay, so we reject. Okay. All right, so that's our calculating the p-value for the two-tailed alternative. Okay, so that's case 1. So case 1, case 2, and case 3. Okay, so in case 2, notice that with all of the null hypotheses, the nulls always include the situation of 0, the case of 0. So in case 2, then we have a null hypothesis that says that the mean is less than or equal to 0. Okay, so now we have this distribution under the null. Okay, so we still have this 0 here. And now we're only interested in the alternative where it is greater than 0. Okay, so we're really interested in this side over here. Okay, so all of this area here is where we are. This is going to be our rejection region. Okay, so remember that with the two-tail, if it was in here or here, we can reject, so we include both. But in this case, we're only going to include this area. Okay, so now how do we do this? Well, there's a couple of different ways. So remember that our test statistic was 2.8. So it's still at 2.8 here. Now, remember that this is a PDF, so the total area under here is going to equal 1, but the norm_dist function gives us the area to the left of whatever number we put in, so we can do 1 minus all of this area here. So whatever the cumulative, norm_dist up to 2.8, etc. Okay. The other way we can do it is we know that this is symmetrical, so we can just say, okay, well, this area over here is going to be the same as this area over here. So we could just just find this area. It's going to be the same. It's going to be a positive amount, right? So it doesn't. These two will give us the same values, and I'll go ahead and prove that. So, okay, so we'll do it this first way first. So, just finding this, the probability of observing a value over here on the right. So this is going to be 1 minus norm_dist, okay, and our value is 2.8. Mean 0, standard deviation of 1, and cumulative is always true. Okay. All right. So 0.0025. Okay. We have, we've seen this before, this area before. It was the same one that we got over here, but now we are just going to, we only care about one of these tails, because we're only going to reject if it's in this area here. Okay, so now in this case, our p is 0.0025. Okay, so notice that we have a smaller p-value than we had in the two-tailed test. Okay, so once again, this is also less than alpha, so we're going to reject. Okay, but just make a note that if we are doing a two-tailed test, we need to have a more extreme value than if we're doing just a one-tailed test. Okay. All right. So now case 3. I'm actually going to erase something here just to keep it clear that we are doing. We're just interested in one tail over here. We're going to ignore that. So this is two tail. This is one tail to the right. Now in this case, so in case 3, we have a null hypothesis that the population mean is greater than or equal to 0, and the alternative is that it's less than 0. So now we have this, okay? And what's the probability? So once again, we got 2.8. So we got 2.8. So that's going to be out here again. And we have already calculated the probability of this, of it being out here. But in this case, our rejection region is going to be anything substantially less than 0, right? So we still have a value that's extremely different from 0, but we want to know, how far. So we're going to take the negative of that 2.8, so negative 2.8, and then find the... So we have a one-tailed probability again. So once again, we're just going to be, looking at one of these tails. And so, we've already calculated that twice now. So the p-value there is going to be 0.0025. Okay. And once again, p is less than alpha, so we reject. Okay. Okay, so in general then, the key here with the p-value is it puts a probability of observing a value this extreme. And there's really only two cases. There's going to be the two-tail case and the one-tail case. And basically the thing to remember as a shortcut is that if you are doing a two-tail test where your alternative hypothesis is just not equal to, then that's going to be twice, your p-value is going to be twice what it is under a one-tailed test, because you have to consider both sides, the probability of it being less than or greater than. Okay.